In section 8.5, we discussed the achievability of the information rates distortion function Ri of d. First, recall that the rates distortion theorem says that Rd is equal to Ri of d. Here is the strategy for proving the achievability of Ri of d. First, an IID source xk k greater than or equal to 1 with generic random variable x with distribution px is given. For every random variable x hat, taking values in the alphabet x hat with expected distortion between x and x hat less than or equal to d, where d is between 0 and d max, we will prove that the rates distortion pair ix x hat d is achievable by showing that for large n, the existence of a rates distortion code such that the rate of the code is not more than ix x hat plus epsilon, and the distortion between the source sequence x and the reproduction sequence x hat is less than or equal to d plus epsilon with probability almost equal to 1. And then minimize the mutual information between x and x hat over all such x hat to conclude that the pair Rid, d is achievable. By the definition of R of d, this implies that Ri of d is greater than or equal to R of d. We first describe the parameter settings for the random coding scheme. First, fix epsilon greater than 0 and x hat such that expectation of the distortion between x and x hat is less than or equal to d, where d is between 0 and d max. Let delta be specified later. Let m be an integer satisfying 1 over n times log m greater than or equal to ix x hat plus epsilon over 2 and less than ix x hat plus epsilon, where n is sufficiently large. The idea here is that the rate of the code exceeds ix x hat, but not by too much. Here is the random coding scheme. First, construct a codebook C of an NM code by randomly generating m code words in the alphabet set x hat to the power n, independently and identically, according to px hat to the power n. Denote these code words by x hat 1, x hat 2, up to x hat m. This is illustrated in the following figure. Then review the codebook C to both the encoder and the decoder. The source sequence x is then generated according to px to the power n. The encoder encodes the source sequence x into an index k in the set I containing the indices 1, 2 up to m. The index k takes the value I if a, x and x hat I, that is the ith code word, are jointly typical. And b, for all I prime, if x and x hat I prime are jointly typical, then I prime is less than or equal to I. That is, if there exists more than one I satisfying A, let k be the largest such index. Otherwise, k takes the constant value 1. The index k is delivered to the decoder. The decoder outputs x hat k as the reproduction sequence x hat. Here are some remarks. First, the event k equals 1 occurs in one of the following two scenarios. X hat 1, that is the first code word, is the only code word in C which is jointly typical with the source sequence X. Or, no code word in the codebook is jointly typical with the source sequence X. Second, if k is not equal to 1, then the reproduction sequence x hat k is always jointly typical with the source sequence x. As we will see, k not equal to 1 corresponds to successful encoding, and k equals 0 corresponds to an encoding error. The performance analysis is done in a number of steps. First, recall that the event k equals 1 occurs in one of the following two scenarios. x hat 1 is the only codeword in the codebook which is jointly typical with the source sequence x. Or, no codeword in the codebook is jointly typical with the source sequence x. In other words, if k equals 1, then the source sequence x is jointly typical with none of the codewords x hat 2, x hat 3, all the way to x hat m. We will show that the probability that k equals 1 can be made arbitrarily small. Define the event E sub I to be the event that the source sequence and the ith codeword are jointly typical. From the discussion in step 1, we see that the set k equals 1 is a subset of E2 complement intersect E3 complement intersect all the way to EM complement. Since the codewords are generated IID, conditioning on a particular source sequence X, the events EI are mutually independent and have the same probability. Then for any particular source sequence X, the probability that k equals 1 given x equals x is upper bounded by the probability of E2 complement intersect E3 complement intersect all the way to EM complement, conditioning on x equals x. Because the events E2 up to EM are independent, this probability is equal to the product from I equals 2 up to m, the probability of EI complement given x equals x. Furthermore, because all these events are identical, this is equal to the probability of E1 complement given x equals x to the power m minus 1. Or 1 minus the probability of E1 given that x is equal to x to the power m minus 1. We will focus on those source sequence x in the set S sub x delta sub n, where the S set is equal to the set of all typical x sequence such that there exists at least one typical x hat sequence which is jointly typical with that x sequence. Because from proposition 6.13, we know that the probability that the source sequence is in the S set is approximately equal to 1 for large n. For an x sequence in the S set, we obtain the following lower bound on the probability of E1 given x is equal to x. First, the probability of E1 given x is equal to x is equal to the probability that x and x hat 1, that is the first codeword, are jointly typical. This is equal to summation p x hat, such that x hat is in the conditional typical set T x hat given x delta sub n of x. By the consistency of strong typicality, if x and x hat are jointly typical, then x hat is also typical. And so by the strong AEP, px hat is lower bounded by 2 to the power minus n times entropy of x hat plus eta. Now by the conditional strong AEP, if the conditional typical set is non-empty, which is the case, then its size is lower bounded by 2 to the power n times entropy of x hat given x minus xi. Rearranging the terms, we have 2 to the power minus n times entropy of x hat minus entropy of x hat given x plus xi plus eta, where hx hat minus hx hat given x is equal to ixx hat. And we define xi plus eta to be zeta, where zeta tends to 0 as n tends to infinity and delta tends to 0. Now from step 5, we have the probability that k is equal to 1 given x is equal to x is less than or equal to 1 minus the probability of E1 given x is equal to x to the power m minus 1. Applying the above lower bound on the probability of E1 given x equals x, we obtain the upper bound 1 minus 2 to the power minus n times ixx hat plus zeta to the power m minus 1. Now recall that we chose m such that 1 over n log m is greater than or equal to ixx hat plus epsilon over 2. This implies that m is greater than or equal to 2 to the power n times ixx hat plus epsilon over 2. In step 8, we obtain an upper bound on the probability of k equals 1 given that x is equal to x. Taking the logarithm, we obtain that log of the probability that k is equal to 1 given x is equal to x is lower bounded by m minus 1 log of 1 minus 2 to the power minus n times ixx hat plus zeta. Now observe that this logarithm is negative, and so by applying this lower bound on m, we obtain the upper bound 2 to the power n times ixx hat plus epsilon over 2 minus 1 times log of 1 minus 2 to the power minus n times ixx hat plus zeta. Now for this logarithm, we apply the fundamental inequality to obtain the upper bound minus 2 to the power minus n times ixx hat plus zeta. When this term is multiplied by this term, this ixx hat cancels with this ixx hat. And so we obtain 2 to the power n times epsilon over 2 minus zeta. And the other term is obtained by multiplying minus 1 by 2 to the power minus n times ixx hat plus zeta. Now let n be sufficiently large and delta be sufficiently small so that epsilon over 2 minus zeta is greater than 0. So as n goes to infinity, this tends to infinity and this tends to 0. Then the above upper bound on log of the probability of k equals 1 given x equals x tends to minus infinity as n tends to infinity. That is, the probability of k equals 1 given x equals x tends to 0 as n tends to infinity. This implies that for a sequence x in the S set, for sufficiently large n, the probability of k equals 1 given x equals x is less than or equal to epsilon over 2. Now it follows that the probability of k equals 1 is equal to the probability of k equals 1 given x equals x times probability of x equals x over all x in the S set, and we take the same summation over all x which are not in the S set. Now the probability that k is equal to 1 given that x is equal to x where x is in the S set from step 11 is upper bounded by epsilon over 2. For x not in the S set, this conditional probability is upper bounded by 1. Of the probability that x is equal to x over all x in the S set, is simply the probability that the random source sequence is in the S set. And the summation of the probability of x equals x for all x not in the S set is simply the probability that the random source sequence x is not in the S set. Now the probability that the source sequence is in the S set is upper bounded by 1, and the probability that the source sequence x is not in the S set by proposition 6.13 is upper bounded by delta. And so, we have obtained that the probability that k is equal to 1 is upper bounded by epsilon over 2 plus delta. By letting n's be sufficiently large and delta be sufficiently small, so that epsilon over 2 minus zeta is greater than 0. Recall that we need this condition to ensure that for sufficiently large n, for a sequence x in the S set, the probability that k is equal to 1 given x is equal to x is less than or equal to epsilon over 2, and this contributes to the term epsilon over 2 in the above upper bound on the probability of k equals 1. At the same time, we let delta be sufficiently small so that delta is less than epsilon over 2. And so we obtain the probability that k is equal to 1 is less than epsilon.